In Newtonian gravity, planets orbit the stars in ellipses. Now let's take the velocity vector at every point on the orbit and put their tails together. You'll notice that the tips actually trace out a circle. This is known as the circular hodograph and is the starting point of understanding the hidden 4D rotational symmetry in gravity. But why do the velocity vectors trace out a circle? What does symmetry mean in this context? And where is the fourth dimension? It's not time, by the way. But let's first see how this circular hodograph came to be. A key property of orbits is that the line from the star to the planet sweeps out area at a constant rate. This isn't too difficult to prove, and here is Newton's original argument. Let's say the star and the planet were in this configuration, and after some small period of time delta t, the planet moved slightly. The area swept by the line is this shaded region. If there had been no force acting on the planet, it would have moved the same distance for the next delta t period. The area swept in these two time frames would have been equal, as both the base and height match each other. When gravity kicks in, the position of the planet after 2 delta t would change slightly, but since gravity pulls the planet towards the star, the change is parallel to the line at time delta t. So the brown region is the area swept for the second delta t time period. With the parallel line construction, we see that the brown area is the same as the previous purple area because of the same base and same height. But we know that the purple area equals the green one. So even under gravity, the area swept in the two time frames are the same, and the area sweeping rate remains constant throughout. Let's denote this rate as L over 2m, where m is the mass of the planet. Since we have shown this sweeping rate is constant, L is also a constant, and in fact, this constant is known as angular momentum. Let's think about area sweeping in a slightly different way. In a small period of time delta t, the region swept out is very close to a circular sector, with the radius r being the distance between the star and the planet, and the angle subtended denoted as delta theta. The area of a sector is half radius squared times the central angle, and in this case it is half r squared delta theta, so the area sweeping rate is half r squared d theta by dt. Since the sweeping rate is L over 2m, we have L over 2m equals half r squared d theta by dt. We're about to do some simple algebraic manipulation by multiplying both sides by 2 over r squared. We then have L over mr squared equals d theta by dt. Next, we multiply both sides by m over L so that we obtain an expression for 1 over r squared. The reason we want this expression is that it appears in the equation of motion for the planet. The right-hand side is the force of gravity, where we denoted gmm as k for simplicity, and the left-hand side is just mass times acceleration, but we are going to rewrite it as the rate of change of momentum p. As for the right-hand side, we can use the previous expression for 1 over r squared to rewrite it. So in a small time period of delta t, the change in momentum equals minus mk over L times change in theta times the unit vector r. This is what we need to explain the circular hodograph. Suppose the current momentum vector p points in this direction, and after some time delta t, momentum points in a slightly different direction, with the difference being delta p, whose magnitude is mk delta theta over L as seen in the expression we derived. The next time step is deliberately chosen not to be delta t. Instead, we want the same change in theta, which might mean a different time interval. That makes the two delta p's have the same magnitude. Since these delta p's point in the opposite direction as the position vector, the angle between them is also delta theta because the position vector has shifted by this angle. If we keep doing this, incrementing not by the same time interval but same change in theta, then these delta p's will culminate in a circle, demonstrating the circular hodograph. This might have sounded a bit hand-wavy, but it can be formalized by turning this expression into a differential relation after dividing by delta theta. This r hat is just the unit vector for the position and can be written as cos theta sine theta on the 2D plane. Now all you need to do is to integrate this with respect to theta, which should be quite straightforward, and we end up with two parts. The first part involves sine theta minus cos theta, which already indicates the hodograph forms a circle. The prefactor indicates the radius of this circle. The other part, which is an integration constant, is the center of the circle. This is essentially the same as the geometric argument, just rephrased differently. In any case, we've argued why the velocity or momentum vectors trace out a circle. Before we link it to a 4D symmetry, we first have to answer what symmetry means in this context. Generally, symmetry refers to transformations that preserve certain structure. Like this pentagon, whether it is reflection or rotation, these are transformations that leave the shape unchanged. In the Newtonian gravity context, we should define what to transform and what structure we want to preserve to count as symmetry. For this video, we consider transformations that act on position and momentum spaces together. More specifically, they act on the 6-dimensional phase space, and these are best thought of as projections onto the first 3 coordinates and the other 3. So a transformation could even swap x to be p and p to be minus x, and this will be a valid transformation in the 6-dimensional space. The next thing to unpack is what structure we want to preserve in this physical context. A physical orbit involves an ellipse in the position space and a circle in the momentum space. This was the circular hodograph we showed before. We want the transformation to give us another set of points to form another physical orbit. But if we define it like that, there are too many symmetries, so we require the energy of the orbit to also be preserved. This is what symmetry means in this context, a transformation of the phase space which sends physical orbits with energy E to other physical orbits with the same energy. Under this definition, if I simply rotate position and momentum spaces simultaneously, I will just rotate the orbits, and the energy doesn't change. I can even rotate to some other planes, and it should still be a symmetry with this definition. But there is a different kind of transformation you can do. Take a point on the orbit and the corresponding momentum, and translate it across the circle centered at the star. But why do we do this? Energy is given by this expression, where the first term is the kinetic energy, rewritten slightly from the more familiar half mv squared. The second term is the potential energy, where gmm is denoted as k, as before. While translating across the circle, we chose a point equidistant from the center, so the potential energy term, which depends on distance from the origin, remains unchanged. We also didn't touch the momentum vector, not even its direction, so the kinetic energy also remains unchanged. Overall, energy hasn't changed, and the resulting orbit should have the same energy as before. This transformation results in a family of orbits with the same energy, and they all have different shapes. Of course, we don't have to restrict ourselves to a plane, and you can transport this point across this vertical circle instead. This time, we end up with another family of orbits with the same energy, and once again, they have different shapes. These transformations turn out to correspond to some 4D rotations, which are easier to see in momentum space, so this is where we're going next. Let's go back to some calculations we did before. We've used relatively simple integration to show the hodograph is circular, and in particular, we showed that the radius of the circle is mk over L. This will be useful later on. The other useful fact is the constant area sweeping rate being L over 2m. In particular, let's consider the sweeping rate when the planet is the furthest away, also known as the aphelion. At this point, the velocity vector should be perpendicular to the line joining the star and the planet. Calling this vector VA, where A stands for aphelion, in a small period of time delta t, the planet traveled a distance of VA delta t. Let's also denote the distance from the star to be RA. Then the area swept during this time is half base times height, which is half RA times VA delta t. So the area sweeping rate is half RA times VA. After a couple of steps, we can reach the statement where L equals RA times PA, with PA being the momentum at the aphelion. This is the statement that will be useful in a minute. For now, let's go to the circular hodograph, noting that the magnitude of the momentum vector at the aphelion is the smallest out of all the others. The total energy at this point is PA squared over 2m minus K over RA, and we can use the relation we previously derived to rewrite the potential energy as minus kPa over L. With this, we can already forget about this relation L equals RAPA. The next step is to multiply both sides by 2m, and then complete the square on the right-hand side. This can be achieved by adding the term m squared k squared over L squared on both sides, because then the right-hand side is a perfect square. Specifically, it is the square of PA minus mk over L. Two final touches on this expression. The first one is just swapping the order of subtraction within the square, which doesn't change the value, and the second one is to move 2me onto the other side. Phew, that was some work, but hopefully each step has been tiny. What follows is a geometric meaning to all these. Since the radius of the circular hodograph is mk over L, this segment has length mk over L, so the green segment has length mk over L minus PA. Now let's draw a perpendicular line to intersect the circle. Since the hypotenuse of this right-angle triangle is the radius, it has length mk over L. We can finally try to interpret this relation we derived before. Basically, this is the Pythagorean theorem on this right-angled triangle, and we can determine the length of this blue segment, which is square root of minus 2me. It can be jarring to see a negative sign in the square root, but rest assured that e is negative for an elliptical orbit, so we are fine. If e is not negative, we need to modify the analysis, and I will talk about it at the end. As a little summary, if you see a circular hodograph, identify the origin where the vectors emanate from and the center of this circle. Draw a little segment joining the two and the perpendicular line from the origin. We've shown that either of these two segments has a length of square root of minus 2me. Since symmetries preserve energy, it leaves this length unchanged. A simple rotation like this doesn't change this length, so rotation is a symmetry. But there is another transformation, where I change the size of the circle, but fix these 2 points on the blue line. These transformations still count as symmetry because these segments' length, hence energy, remain unchanged. In position space, this transformation was what I said to be a 4D rotation, just that it is easier to visualize the fourth dimension in momentum space, as the orbit in momentum space is a circle, not an ellipse. And we're about to see this fourth dimension now. The hodograph is on a plane and would have looked like this in 3 dimensions. For the transformation we considered, these 2 points at the end of the blue line stay fixed, and we pick them to form the diameter of a sphere. The hodograph can be mapped onto the sphere via something called stereographic projection. Basically, for every point on the hodograph, draw a line to the north pole of the sphere. The intersection of this line with the sphere is the stereographic projection we want. Do this for all the points on the hodograph, and you will see a circle on the sphere. This is not just a circle on a sphere, but a great circle. You often hear this as straight lines in the context of flight paths on Earth. The hodograph transformation we saw earlier corresponds to rotating the great circle on the sphere, even though it doesn't look like a rotation at all if we stay on the plane. I want to emphasize that this is already a 4D rotation, just using a 3D analogy. No matter how I rotate the original hodograph in 3D, I can't possibly change the size of the circle, because a normal 3D rotation doesn't change sizes. In order to see something that changes the size of the hodograph, you need an extra dimension for the stereographic projection. In other words, it's the 3D shadow of a 4D rotation that changes the size of the hodograph. The previous illustration was an analogy depicting a 2D shadow of a 3D rotation, because generally it's really difficult to imagine this as a 3D shadow of a 4D rotation. After all, you can't even visualize the 3-sphere in 4D. But let's go back to the lower dimensional analog. Because these are great circles, the equivalent of a straight line on a sphere, they are also the trajectories of a free particle constrained on the sphere, similar to how straight lines are trajectories of a free particle in a Euclidean space. So, any trajectory of a particle under Newtonian gravity with some negative energy E can be mapped to some circular hodograph with the property that a certain line segment has length square root of minus 2me. This can then be mapped to trajectories of a free particle on a sphere via stereographic projection. Again, this should be understood as the 4D sphere or the 3-sphere. Since these trajectories on the sphere have a 4D rotational symmetry, we say that the original setup also has a 4D rotational symmetry. The first person to mention this seems to be Vladimir Fock in 1935, but he was doing quantum mechanics. A hydrogen atom can be thought of as an electron orbiting the proton, and then you treat it quantum mechanically somehow. Fock discovered that this is equivalent to solving the free electron wave function on a 3-sphere, which is actually easier. The classical version wasn't explicitly mentioned until 1966, so it's a weird case that the quantum analog was found before the classical one. I'll leave you with a very brief overview of what happens if we don't have an elliptical orbit. When the energy is high enough, escape is possible and a hyperbolic orbit is formed. Similar to the elliptic case, the hodograph is still circular with two main differences. The first one is that the circle is incomplete. There are some parts of the circle that are inaccessible with this hodograph. The second difference is that the origin is outside of the hodograph even after you complete the circle. With similar arguments in the video, you can also show these two blue segments have length square root of 2me. So the symmetry in this hyperbolic case are all transformations that keep the tangent lengths fixed. It turns out that there are also some higher dimensional symmetry involved, but this time it's not a sphere, it's a hyperboloid, where the length of the blue tangents is the distance between the center and an apex of the hyperboloid. We do a stereographic projection here as well. From an apex of the hyperboloid, draw a line to an arbitrary point on the hodograph. The intersection of this line with the hyperboloid is the projection of this point. If we do that for all the points on the hodograph, we end up with what's basically a straight line on the hyperboloid. That's why the symmetries for the hyperbolic case correspond to 4D hyperbolic rotations. More details in the description. So that wraps up our exploration of the hidden 4D rotational symmetry of gravity, as well as this video series. I hope this series gives you the impression that there can be many more surprises to discover, even in classical mechanics. As always, thanks to the patrons, don't forget to like and subscribe. Merry Christmas, everyone!